Welcome back to The Explainer. We are jumping right back in to kick off part 2 of our Vessel Architectures module. If you've been following along, you know we've been breaking down exactly how these immense offshore structures are physically arranged. Today, we're tackling our final rig type, and then we're going to trace the actual electrical path from raw fuel all the way to the drill floor. Let's get right to it.
Okay, let's start with a lightning-fast recap to set the stage. In our last explainer, we contrasted the two massive floaters. You've got the semi-submersible, which places its power generation incredibly low in the pontoons for stability, giving us those short vertical cable runs. Then you have the drill ship, built like a conventional ship with generation aft or midships, meaning massive fore-to-aft cables. It's the same drilling gear, but completely different electrical plumbing.
And that brings us to our third and final architecture, the jack-up rig. Now, the fundamental difference here is that this rig does not float while drilling. It's a standing rig. It literally jacks its compact main hull clear out of the water on 3 massive legs planted firmly on the seabed. Now, because those incredible steel legs have to physically bear the weight of the entire rig while reaching the bottom, jackups are typically limited to shallower waters, usually under 150 meters.
Ultimately, no matter what kind of rig you're on, semi-sub, drill ship, or jackup, the electrical systems are there to do serious mechanical work. We're talking about powering the drawworks, rotating the drill string with the top drive, and circulating fluid with massive mud pumps. Our jackup has to power these exact same massive, heavy-duty components, but it has to do it within a drastically different physical space.
Because a jackup's hull is so compact compared to a floater, everything gets squeezed. I mean, the generation, the switchgear, and the drive rooms, they're all tightly packed onto just 1 or 2 decks, completely confined within the footprint of those 3 legs. This extreme, almost claustrophobic density makes the initial engineering and, frankly, the long-term physical maintenance of these spaces incredibly challenging. But here is a crucial point to remember. Do not confuse capability with simplicity. Just because a jackup operates in shallow water and has a small hull, that absolutely does not mean it has a simpler electrical system. The variable speed drives, the drilling motors, and the drawworks controls crammed inside those tight decks, they are the exact same advanced high-tech systems used on ultra-deepwater floaters. They're just packed into a much, much smaller box. To really lock this in your memory, think of it like a real estate analogy. You're basically fitting the same furniture into 3 different homes. A semi-submersible is a townhouse. Generation is low, and the drive rooms are stacked vertically right above it. The drill ship is a shotgun house. Everything is in a long line, with endless hallways. And the jackup? Well, it's a studio apartment. Highly compact, everything is right next to each other, but with way less room to maneuver when you actually need to fix something. So let's do a quick check and put this logic to the test. Based on those physical shapes we just discussed, if you had to match the rig to its power layout, which of these 3 hull types has the shortest average cable run? If you guessed the jackup, you hit the nail on the head. By keeping the generation and drive rooms incredibly close together in that studio apartment layout, the jackup trades a painfully tight physical design space for the distinct advantage of having the shortest average cable runs. It's a direct trade-off against the drill ship, which obviously has plenty of room but has to battle massive voltage drops over its long fore-to-aft cable trays. So, just to wrap up the physical side of things, coming into this, you might have known rig components by name only. But now you can look at a silhouette of any of these 3 rigs and instantly predict its internal layout. Semi-suds generate low with short vertical runs, drill ships generate aft with long runs requiring heavy cooling, and jackups feature a compact hull with the absolute shortest cable runs. Okay, you've mastered the physical layout. Now, let's switch gears and trace the actual power path. We know where the rooms are, but let's actually follow the journey of a single electron from raw diesel fuel all the way to drawworks torque. It follows a very strict 5-step flow. First, it starts at the diesel generators. Next, it hits the high-voltage switchboard. Third, it flows through the transformers to step the voltage down. Fourth, it enters the converter panels. And finally, step 5, it drives the actual drilling motors.
I absolutely love this next part because we can connect that conceptual 5-step path directly to a real-world single-line interface. This grounds the theory in exactly what operators and commissioning engineers are seeing on their screens on the field. You can literally trace the flow right from the main supply incomers acting as the switchboard, through the transformers, into the diode bridges and common DC bus of the converters, and finally down through the inverters to power the specific top drive, drawworks, and mud pump motors. It maps perfectly.
But there is a critical engineering reality here that you must never forget: the weak link warning. Every single watt that turns your drawworks goes through that entire 5-step chain.
That means the entire power path has to be sized together. If you have an undersized transformer or even a poorly rated feeder breaker, it's going to instantly throttle your drawworks performance. It really doesn't matter if you bought the absolute most expensive top-tier variable speed drive on the market. A great drive simply cannot overcome a bottleneck upstream.
So, we can successfully trace power down to a single motor. But what happens when you scale up and need to run 3 massive mud pumps at the exact same time? Do you give each motor its own independent power system, or do you build one shared DC bus and split it 3 ways? That question right there defines the massive conflict between single-drive and multi-drive topologies, and that is exactly what we're going to tackle in our next explainer. See you then!